Okay, you can start.
Okay. Yeah. Hello. Today I will talk about binary counters and the bit probe model. The general idea is what happens if we want to have a counter to have a representation of integer numbers of a fixed size, which can be incremented or decremented without reading all the bits. And so my main result will be the lower bound on how many bits we can read. We have to read. So what is the basic problem and what is the model? The problem is that we have a range of natural numbers. Most of the time it will be, oh wow, maybe even better to write like that, of large and natural numbers. We have a range of large and natural numbers. Most of the time are not completely always, and large n will be a power of 2. And we want to represent the natural numbers in this range as sequences of bits, but we want to have cheap increment and decrement operations. In what sense cheap? When we have a operation, we can express it in different models. In this case, we will say that we are allowed to read bits one by one, and we are allowed to read them adaptively, and we count how many bits we read inside a single increment or decrement operation. In other words, our representation will have the mapping from the range of the numbers we represent to sequences of bits of fixed length. In the more main case, we will have a range of length 2 to the power of n, and we will use n bits. And we have a mapping, and we can code it. And then we have two operations, increment and decrement. Well, they behave in a similar way, and bound works even if we consider only the increment. And so we have an increment operation which means we have a representation, and we want a representation of the next number, saying that the next number after the largest one is 0 again. And the increment operation is represented as a binary decision tree, which means we say, okay, like here we say read, third bit. It can be either 0 or 1, and if it is 0, we say read second bit. If it is 1, we say, for example, read fifth bit. And now, if the fifth bit is 0, we can say write 0 to the third bit. So of course, we have a larger tree, and we have a lot of leaves, and in every leaf we have instructions what to change. And each internal node is an instruction which bit to read, and depending on this bit, we proceed.
So in the leaf, you can change more than one bit.
Yes, I can. Yeah.
And Sasha also has a question. Whether the presentation of the number of a number must be unique or not?
Well, the main case will be, as I said, when we have 2 to the n numbers and n bits, and so in this case it has to be unique for other reasons. And in general, well, if we start with any representation of 0 and then we just use increment, if we have non-uniqueness, we have to have non-uniqueness everywhere. Well, either we have connected component of via increment, or we have at least two representations of every number. But if we have two representations for every number, these are representations that are so inefficient that we won't talk about.
So, for example, it's not allowed to remember which bits were read.
Yes, well, during the increment we remember which bits we have read, but the representations where we have a lot of representations of the same number, we will just not use such representations. Okay, so well, we can ask how many bits we read, we can ask how many bits we write. So what is known about that? What has been known for a long time? There is the patent of Greya from the year 1953. Which says that even if we don't care about how many bits we read, but we care how many bits we write, we can only write 1 bit per increment. So we can, if by the implementation of Greya code, read all the bits, but write only 1 bit per increment.
And the length is n.
Sorry?
And n bit is used.
Yes, it is a precise code which uses all the possible combinations to represent different integers. So it is a space optimal, and it only writes 1 bit per increment, and it reads everything in some cases. Then there is a paper with a lot of authors. Let me even read the list, because I don't really remember it by heart. So it turned out that despite the intuitive so it turns out that so it is Brodal, Brief, Pendy, and Setti in quite recently. It turned out that it is not necessary to read all the bits. It turned out that it is possible to n-1 read and I think right. Yeah, here I'm talking about worst case complexity. So the worst of all the increments during a cycle will have this complexity. It is not average, it is exact worst case. So it is enough to have that many reads. So you can say 1 read in the space optimal case. You use all the combinations to represent unique numbers, and you can increment while skipping not skipping, by not reading the last bit, but last is different, of course, on every increment. Yeah. And
Initially, this is for the increment operation.
In both increment and decrement have the same complexity.
And also for deciding whether the number is 0 or not.
Well, for deciding whether the number is 0 or not, in the space optimal code, you have to read all the bits. Because every combination represents a different number, and if you haven't checked 1 bit, it still could be a different number. Then there is paper by Trenet, exactly Trenet. Where it is n-1 bit and 1 right. And then there is also a paper by Raman and Ro. Which says if you have one extra bit, one extra storage bit. So our representation uses n+1 bit for numbers from 0 to the n-1. And then in the worst case it is log. So it is log plus constant reads in the worst case if we use the one extra.
Nish Sasha has again a question. How this all is related to the Turing machines? Assume that Turing machines have one tape, linear memory, linear space, and it should increment and decrement, and it says считать туда-сюда. I don't understand actually. Decrement and decide возвращение в return it to 0 and reaching to the n in order log n steps.
Well, I think that Turing machines are not a closed model for this specific task for the following reason. In the Turing machine, we have linear order on the bits, and here we have random access. The problem is that if you want to skip reading a bit in the middle of the representation, for the Turing machine, we have a problem. We need to pass it when we go from the left side to the right side. So Turing machines just behave differently. The random access is crucial here. Well, I'm not sure I'm answering the correct question, but I'm not sure what exactly. Yeah.
Is this harder, I mean, for Turing machine, or easier?
With the binary tape?
Or it's completely different?
It's completely, well, here in the Turing machine must read in order, so in the sense that it cannot just jump over one bit. And that means that the complexity for Turing machines is quite a significantly different notion than random access when we are talking in this situation, when we want just to skip one bit. And for Turing machine, it is hard just because it has to transport itself. Not just read the bits, but also transport itself. Okay, so the summary is that we know. So the summary is that overall you can save one bit while still having gray code and having one write and n-1 bits for an optimal representation where you use all the combinations for unique numbers. And if you take one extra bit, you have logarithmic complexity, and of course there is constant number of bits. And in reality, in this paper, there were constructions which don't use exactly one extra bit. They use one extra bit, but then they provide more valid representations in the sense that they skip on not half of all the code space, but they skip just a small fraction of the code space. And so, yeah, so if you have some extra space, you can have logarithmic complexity in terms of reads. And if you don't, the best known upper bound is still even now n-1. So this is, and is there a lower bound? Well, of course, there is a logarithmic lower bound in the sense that if you read less than a logarithmic number of bits per increment, that means that the entire decision tree has less than logarithmic width or height, and then it has width less than n, and then it means that we cannot read some of the bits, which means that these bits are useless. And so there is a trivial logarithmic lower bound. And the question is, of course, that when you have logarithmic lower bound and n-1 is an upper bound, there is this question of what is correct complexity and what can you do in the space optimal case when you must use all 2 to the n combinations.
Sorry, you mean if there are less than n leaves, then there are 2 strings?
If there are less than n strings,
Which come to
that means that the total number of internal nodes is also less than n. That means that there is a bit which is never mentioned in the tree.
Okay.
And if we don't read some bit, what we even store it.
Or you can say that just there are 2 strings which come to the same leaf, and then the result is the same for them.
No, the same, they are changed in the same way, but yeah, that means that we have a disconnected case. Yeah, but in any case, we have bits which we never read, which means that we can just, they don't never change, and so we can just erase it.
So why they don't never change?
Mention that we have height less than logarithmic n.
Yeah.
That means that we have less than n leaves. That also means that we have less than n internal nodes. But to read a bit, we need to put it into its number or some internal node.
So assume that we never read the first bit.
Yes.
What is the problem?
If you never read the first bit, that means that the first bit is never changed.
Why?
Because
what if you
right. If you don't read it but write it, okay. If you never read it but write it, it means that, okay, yeah, that's true. Well, okay, if we don't write, yeah, I just
Онлайн трудно понимать. Сейчас я в микрофон скажу. Что вы сейчас рассказываете? В каком месте вообще доклада? Вы вот доказываете, объясняете, как Раман Мунро или что?
Нет. I'm at the point that after the overview, I'm explaining the trivial lower bound.
Объясняется тривиальная нижняя оценка. А какая? Логарифмическая. На что? На риды? Значит, тривиальная оценка на количество чтений log n, я думаю, ты сам это понимаешь.
Я пока не понимаю.
Well, yeah, okay. If we go more carefully, if we want to use all 2 to the n combinations to represent unique integers, in this case I can just say that I have, I need to have unique representation, so increment must be a permutation, and then if we have a permutation, that means that two different sequences of bits cannot be incremented to the same. That means that we must never write bits that we never read, but that we haven't just read. We are only allowed to change the bits that we know.
That was not read.
Yes, if we haven't read a bit, if we write it, we break the bijection property. It is not a permutation.
We will write a bit which was read.
No. I mean, if you have read, for example, you have this string like that, we have read 1 here, 0 here.
Yeah.
If we write 1 here, we write it regardless of what was here.
Yeah.
And if all combinations are possible, then we have the same output for two different strings.
But if they differ in some other bit, not that one, where you...
But the point is, if we use all the combinations, then I have combination which has these red bits and one here, and I have combination which has these red bits and 0 here.
We should consider now the case when you have m cells.
Yes, I have n cells and
Exactly,
to the n
not
and
more.
to the n integers, yes, because
okay, so and the result will be the same.
yes, the result will be the same because it doesn't depend on what was here, and we destroy the difference.
Okay.
And so in the space optimal case, we can write what we have read, and so if we don't have enough internal nodes, we just ignore some of it.
In this setting, we are not allowed to write the negation of what is sitting in this particular bit, right? Because otherwise your argument wouldn't work, right? So you have always writing something.
Yes, that's good. On the other hand, if we never read some of the bits, we also can go the other way around. If we never read some of the bits, what does it mean? That it means that we can just ignore writes there, because they will never be read, and so the sequence of increments will be the same, and will loop before, well, even if they change during this, we can just ignore this, and the sequence of the length of the cycle will be the same. They are never read.
If you don't write.
If I never read some cell, I can just ignore writes there, because the length of the cycle depends on the things that I can sometimes check. Well, eventually we start from somewhere and do increments. And then, and imagine that I go through some states via increment. And let's, now I say that if I have come to the same state,
Then the cycle should be
imagine, no. I have come to the same stage, not in the global sense, but only in the sense of the entries which are read during increments.
Okay.
Ignoring all the right only points. Now let's go around this cycle 2 times. I say that on the second time, the entries which are read, they have been changed in the same way, because it is the cycle from their point of view. And the points that are only written, on the second pass, they are the same as on the first pass. Well, maybe the second and the third pass. Because if they're written, if they're never touched at all, they just don't change. If they're written on the first pass, then this cycle will change them in the same way on the second and on the third pass. And so, if something is right only, it doesn't change the stable length of the cycle.
So you mean you will obtain a cycle
Yes.
less than to the end?
Yeah.
If you take like the third cycle or the fourth.
Yes. I also say that my cycle will be the same as if I only use the entries which are read.
You can't use, I think that you cannot use source.
Yes. Here I can use the infinity source.
Misha, what was it? Have you been explaining the same Logan bound to Sasha?
Another.
Another.
No. It was a slightly another group which can also be used in in a slightly more general setting, when I don't claim in advance that I have to the n codes with n bits. I didn't use how many codes I have. I didn't use that I have an exact permutation. So the point is that, okay, so we know if we have one extra bit, we know that we have logarithmic, we now have logarithmic lower bound and logarithmic upper bound, and they differ by constant. And if we have space optimal representation, exact case, then we have n minus 1 as an upper bound and logarithmic lower bound from here to here, and they differ exponentially. And so my result that I will present is that in reality, if we have space optimal case,
You should please write down your
Yes.
result exactly.
yes, that's the, I'm looking where to put it from here. In space optimal case, and it's and we have to represent to the n numbers
To the n or to the n minus 1?
from 0 to the n minus 1.
I mean minus 1 in the x.
Oops, sorry.
Okay.
In the space optimal case, we have to read at least half n rounded up all the way, no, not up. I think, yes. So we have a linear lower bound on reads as we have a linear upper bound. And it turns out that exactness is indeed used in the proof, and it turns out, of course, that, well, it is important that we have a permutation. We have a permutation, and we have a permutation of an even length. And because we have a permutation of an even length, we can use the permutation theory. We can use the notion of the sign of the permutation. And this means that we need to obtain an odd permutation, and I will show that obtaining an odd permutation without reading a linear number of bits is impossible.
You do not understand what is permutation.
No. Now
We don't need to understand it now.
Yeah, it is just, you know, an announcement of what techniques the group will use without any details. And now I will give the real
And also,
and the real
the title. It's not important for now. Okay.
not yet. Okay, so okay. So, how I will interpret the representations of the length of n. So, well, I will use. Okay. So I have the inc, which works, the increment operation, which works on the codes.
I'm sorry.
Yes.
Who is not owned? Can you repeat the definition of representation?
Well, the representation itself is just a mapping which, well, in this case, it's just a mapping which gives for every number from 0 to the n minus 1 some sequence of n bits. there is the canonical binary representation, which is good on average, but in the worst case requires reading everything. But there are also alternative representations, such as Gray code. Gray's code by Frank Gray. And I study how many bits I must read for arbitrary representation.
Misha, another question. So 2 to the n minus 1 can be applied to that number in inc operation or not?
Yes, we can if you give 0 again.
0.
Okay.
And decrement, can decrement 0?
Yes, it will go back to the maximum. But in reality, my bound works even if we have increment without. Okay, so increment is an operation which takes a code of a number and gives us the code of the next number, cyclically next, in the sense of crossing this back to 0. And increment, as we have, as every number is different, it must be a permutation. Because increment is just a, well, if we use all the codes, then how we represent the numbers is a permutation. We just say, okay, we have the canonical binary representation, and we have a permutation, which gives us some alternative representation. And so the increment is obtained from a cycle by multiplying by a permutation and by the inverse permutation. In the sense that increment, like we have our codes in some order. We have code of 0 goes to code of 1, goes to code of 2, and so on, goes to code of 2. So we have code of 0, code of 1.
So the increment permutation.
Yes.
Which is called inc.
Yes.
Oh, okay. This permutation acts on binary strings of length n.
Yes. And it is a cycle of length 2 to n. And now,
Саша опять спрашивает, вы хотите объяснить, что обычный цикл и inc сопряжены перестановкой или что-то еще?
пока что да.
Ну, это вроде всегда, если у нас есть цикл n.
И
Еще какой цикл там есть?
okay. So now I will start using the idea that we don't read everything. And now I will explain the structure of the cycle inc, which is specific to our test. Because before there was no special structure defined to that. How inc works? As I have already mentioned, if we have a space optimal counter, we are not allowed to change the bits that we haven't yet seen. We haven't read. That means that every time when we change, what happens? When we change, we know we change a string. We have a string where we know some of the bits, and we are only allowed to change these exact bits. Such a pattern, well, if we allow they apply the same change to every pattern, to every string that matches this pattern. And how to measure all the strings that match this pattern? If we say that n-bit strings are just a hypercube, well, vertices of a hypercube of dimension n. Because we have what we have. We have 0, 1 to the power n, and we can interpret it as a hypercube. Then, in terms of the hypercube, all the strings that match the same pattern a hypercube of lower dimension. For example, we can say that one of the faces of a real cube is defined by 1 on the, well, in this case 1, or maybe by 0 on the corresponding, on a single position. And in general, if we have long strings and we have a pattern with multiple positions specified, then we have a hypercube of a low dimension chosen among the vertices of a hypercube of higher dimension. Not to say hypercube of a lower dimension every time, I will also call the set of strings or the set of vertices of a hypercube, if you prefer, specified by a pattern. I will call it a block. In terms of, so then we change something here. In terms of this, in terms of the hypercube, this change means that we do a parallel translation of a block.
What is the block say to you?
A block is just a block is just a set of strings which match the same pattern.
Cylinder, another terminology, right?
Sorry?
Cylinder, a cylinder.
Oh, yes. Well, I talked about it as a hypercube, so it's more block than a cylinder, but yeah. Now what we know, we have our binary decision tree. Maybe I should change to another side. Cards, which means I need a large. Then I'm better drawing 4-dimensional cube. So we have a binary decision tree. What it means that we, on the first step, we just cut the entire hypercube, the entire set of strings in half, and read the bit and go into either half. We just cut like that. On the second step, we can read different bits, which means that we can cut one half in one direction and another half in the other direction, and so on. And each leaf in the binary decision tree corresponds to some pattern and corresponds to some block. Well, by definition, because patterns and blocks are all the same for our reasons. And now I say that so when we have the binary decision tree, we have some partition of a hypercube into blocks. So increment, if you have the binary decision tree for inc in a partition, well, it is not exactly this, but it implies a partition into blocks. It's one thing. But what happens next? Next, every block suffers a parallel translation. In each pattern, we change some of the bits without changing the bits out of the pattern, outside the pattern. This corresponds to a translation, or in other words, we can say we have images of the blocks under increment. And the image of a block is also a block because you need to satisfy a pattern. And they are not allowed to intersect because we have a permutation and bijection and the cycle of maximal length.
Who is not allowed to intersect?
Images of two different blocks. Because if images of two different blocks intersect, the original blocks do not intersect. This means that images of two different codes coincide, and this is not allowed.
Misha, what are you claiming now? Just repeat the claim.
My claim is that binary decision tree for increment gives a partition into blocks, and also the second claim now is image of this partition, image under int of this partition is again a partition. Just because we have bijection. Okay, now
Image, about image, can you repeat again? Why the image of the partition is again partition?
well, if we have well, first is also a partition. Image of partition is also a partition under bijection.
Саша, он объясняет две вещи. Во-первых, что это самое binary decision diagram для inc задает разбиение на блоки, первое. А во-вторых, что образ после inc этого разбиения снова является разбиением.
Более того, сейчас я скажу, что это является более того разбиением на блоки. It is also a partition into blocks just for the reason that these are exactly the blocks which inc maps to blocks. Because if we had a pattern and we know that we just change this one into 0 and this 0 into 1, we again have a pattern. And this is how inc acts on the leaves of the binary decision tree diagram, just by definition of our binary decision diagram. So we have two partitions into blocks, before and after the increment. Okay. Now as I promised, but didn't go into detail and didn't explain anything, I promised that I will use the notion of the parity of permutation or the sign of the permutation. And as the definition of the sign of the permutation, I will use the most brute force one, the bubble sort one, in the sense that if I have a permutation, which is from 1 to A0 the parity of the permutation is just the number of I larger than J, AI smaller than AJ. Modulo 2. So I count the number of disorders and ask if it is even or odd. And I hope everyone knows that if I multiply two even permutations, I get an even permutation. If I multiply two odd permutations, I also get an even permutation. And if I multiply odd and even in any order, then I get an odd permutation. Okay, so what is my plan now? The point is that we need some to enumerate all the codes to.
Misha, what is this permutation? Can you say again?
I will look at the inc permutation. I'm looking at the inc permutation, but I will now use the partitions into blocks to define more permutations. I will now define more permutations. Yeah. Well, what is a permutation? In a sense, we just say, well, we can just it is just a way to enumerate all the points in the hypercube. It is or enumerate all the codes. And so, well, what ways of enumerating all the codes we have? We can enumerate all the codes just in the lexicographic order, ignoring our representation. We can enumerate all the codes in the order specified by increment operation and the corresponding cycle. But these two partitions give us one more option. We can pick some random order on the blocks. For example, we have our binary decision diagram. We have the order of leads just if we immerse this diagram into the plane. If we draw this diagram, we have some order on the leaves. And every leaf corresponds to a block. Now we have the following order. What should I delete? Erase. I will call it 4. It is the following permutation, the following order. All codes in the first block lexicographically. Then all codes in the second block, and so
on. Sasha asked a question. So in permutation is a non-cycle. So
yes.
why you are talking about parity?
Oh well, the real plan is to prove the following. I will now define two permutations related to the partition into blocks. And I will prove that each of these permutations is even, and then I will show that I can express in terms of these two even permutations, and then this will prove that inc is actually an even permutation. But it is a cycle of the even length, and so it is an odd permutation. And this contradiction will show that the assumptions about before would be false, and these assumptions would be that my binary decision diagram really has a low depth.
Okay, another question I will ask it in Russian. На каждом шаге мы берем один из блоков, как единое целое сдвигаем его по измеренной координате. Утверждается ли, что он попадает на целый блок, или что?
Its image will be a block, because its image will be a block. It will not be a block of original partition. Но каким-то блоком будет всегда. if we shift a block by changing zeros to ones or ones to zeros in the defined pattern, we always get a block.
It's such a replies. It's certainly a block, but is it a block of a permutation of partition?
Of original partition? No. Well, it is a different, also a partition into blocks. We have two different partitions, before and after. And yeah, so before, and this uses the original partition. And then there is after the same, but using the image of the partition. BDD defines a partition, and when we take an image, it is again a partition in two blocks.
It's not clear why the images of different blocks form a partition.
Because of the size, well, they are not allowed to intersect because image of partition is a, well, image of a bijective image of a partition is a partition. Always, theoretically.
But why can that partition be defined by recursive division?
It cannot be defined by recursive division. I never claimed this, and I will not use it.
Okay.
It is also false. Yes, that's true. It can be made false with some effort. Yeah. Okay. So we have these two enumerations of all the codes according to the BDD and now I will say how increment works. How we can imagine that we know these two enumerations and we want to explain how to calculate increment. Well, how can we explain increment in terms of this? We need to find, we have a code which we want to increment. We want to find in which block of the, in which block it lies initially, and then do the translation corresponding to this block. What it means, we need to see where it, in which block it is in the before enumeration. And then, well, then it is enough to find the entry with the same number in the after enumeration, because it will be at the same position in the corresponding block.
What's going on? In which place of the proof are you now?
I now want to prove that increment permutation can be expressed as a combination of before and after permutation.
So formally, so we have an order. Yeah. Before is an order on binary strings of length m.
Yes.
So and permutation associated with this order gives us for a given string, it gives us like
well, for example, for every number, it gives us lexicographic number of the corresponding code. Like I say that if we discuss as a permutation, then from 0 we go to the initial element of the initial block, and from 1 we go to the second element of the initial block, and so on. And if we talk formally, then we will say that it is. I want to prove that indeed increment is composition of after and inverse before. Why it is so? Well, imagine that we have some codes C,
which
which is called of some number I or something.
Yes, but it doesn't matter at all. Imagine that it is it has a position. It has a position, I don't know, x in block with y elements in the earlier block.
What is the first block in the definition of before? What does it mean, the first block?
Well, binary decision diagram can be drawn, and if we draw, there is leaves from left to right, and each leaf corresponds to a block in the partition. And this is the order.
leftmost leaf.
Yes, yeah, the leftmost leaf.
Okay, but also what is what is the order on blocks for after?
The order on blocks of after, well, each block in definition for used in this partition is an image of the block. I use the same, I use the image of the same order. Okay, if we, okay. So what happens now if we apply before -1 to C? It will give us x plus y. Before -1 of C is x plus y. Because if I ask, well, more or less by definition, because we enumerate all the earlier blocks, then we enumerate the current block until we reach C.
So you just claimed that before of x plus y equals C, and this is because, yeah?
Yes. And now let's look what is after of x plus y. It is the element corresponding to C. It has the same position inside the block. It is the element corresponding to C in the same block because it has the same elements before. So it is the same, the image, well, the corresponding block is the image of the same block. Basically, the idea is that before -1 in combination with after, it preserves the order inside blocks and preserves the partition. And that means that it does the same thing as inc does.
So after of x plus y is somewhere in this.
In the image of the same block, because we have to enumerate all the images of the earlier blocks when we enumerate after, and then we enumerate the image of the block with C. And we will enumerate it until we find the image of C, because the order inside the blocks is not changed by this translation.
Question. Doesn't anybody understand this inequality? Equals after. Oh. Okay, so there are two such persons, and Sasha asks, Sasha, would you like to explain to Sasha Shen now?
Maybe we should ask a preliminary question, then, okay, who understands the notion of before and after representations?
Then we need to start with explanation about before and after. So Sasha, please go there and explain to Shen.
Okay, so oops. So everything. So I guess okay. So first of all, we have a partition into blocks here. Let me draw them. Okay, so each ellipse is a block. Then how I obtain.
So each block is certain set of binary strings.
Of binary strings.
And the difference is that each block is a side number. I mean, it is specified by prefix positions.
Yeah.
And specify the values on those positions.
Mm-hmm. So, and each block here is associated with the leaf of a tree.
Mm-hmm.
Okay. So now,
Such as parity, block is a cycle. Block is not a cycle.
block is just, I say that here on the picture, block is
Ellipse.
ellipse.
Such an ellipse, not a cycle.
Okay. So, and assume that we have ordered blocks somehow, no matter how. And we ordered strings inside the blocks.
And it's quadratic.
Yeah. So,
And that means that we have ordered all the strings of length n.
yeah. So they are listed somehow in such order from left to right. So and it's fixed.
To make it more clear, maybe we need to draw binary decision tree, right?
Oh, I just wanted to draw something below.
Okay, then you will erase it.
I can draw it on lower. Okay, so now we have increment permutation defined as follows, as written here. So, and then we can apply increment permutation to each this binary string.
But have you finished the definition of before?
No.
Okay.
So, and I apply int to every string here. Okay? And so on. And also, so now what is before? Before of x. You just you take you look here and you take the x string.
Sasha, when we just write in, you mean just normally. So you each point represents a string, and int is the next string in the alphabetical order, right? No. What is
Int
this?
is defined as follows. Int maps a code of I into code of I plus 1.
So these points are calls or represent calls? Sasha.
These strings represent calls.
And those domes in ellipses also represent calls.
Yeah. So it just okay. If int is defined as follows, we take a binary string x or y. We then compute a number I such that code of I equals x. Okay, and then you output the code of I plus 1.
So this is the definition of incomplete?
Yeah. Yeah. Okay, so actually this way I think it's like obvious. So before of x. So okay, so we have listed somehow. So here on top we have some enumeration of all strings, such that at first we have that the first portion of the string of the strings are from the first block, then from the second block, and so on. Okay, so before of x is this string, the x string in this enumeration. Okay, and after of x is just a definition inc of before of x. So then, if then it follows that it's false, as far as I can see. Is it true? Yeah. So we apply before -1 here and here. So this is definition of before. I don't know. Is it clear?
Definition of before.
Yeah.
Let me understand. So, before
Is before a number in order behind the law.
So in this picture, can you show how before ends?
Okay. So for example, before of 0, I don't know if you start from 0. Is this string? The first string here. Before of 1 is the second string. And so on. So if the first block contains like p strings, then the before of p minus 1 will be the last string from the first block.
But wait, and your downward arrows, you're to define after.
Yeah. So after is just inc applied to before. So so we have this this equality. But I think what will be used is that after
The partition into blocks.
yeah, so okay, I don't know how it will be used. So I probably think that we now should show that before and after are even if
I will, in reality, what my plan is to say that, okay, now, if this condition is violated, then using the fact that, so that these blocks in the partition have to be very large blocks. Well, because every block is large when it has a few fixed coordinates. So I will prove that if we have very large blocks, then before and after, which are both defined in terms of enumerated very large blocks, cannot be odd. And okay, so does everyone believe in at least one definition of before and after, where this is true or this is true? And also it is clear that before and after enumerate the blocks of the size defined by PDD, while block after block in the lithographical order inside block. It indeed doesn't matter, not important whether to start with defining in terms of blocks and go and proving this, or defining in terms of this and proving that after also you enumerate blocks element by element looks correct. Okay, Then I will move to the, in some sense, to the key part, or maybe the key part is indeed convincing everyone that even before and after makes sense. So now I want to prove that before and after cannot be odd permutation, that they must be even permutation. What is the idea of the proof? What to erase, what to erase, what to erase. Well, combination. As I said, I will. Is the rotation of the camera fine now? Should look slightly to it.
It's okay.
Okay, very good. So as I said, I will use definition which defines the parity of permutation in terms of count of disorders, or inversions if you wish, when we say I smaller than G, after I larger than after G. And now I will just try to count the pair to prove that this is an even number of pairs. I will prove for after because every property of after that I will use is also a property of before.
But maybe you say that in the blocks, strings are ordered lexicographic.
Yes, that I will use.
And why it happens in after?
Well, I mean, it's inside blocks. It is after they are still ordered lexicographically because when we do a parallel translation of the entire block, we have two strings in before. What it means, we have some fixed coordinates and their actual difference, and their actual first difference, for example, here. But then I fix in the same way the fixed coordinates. This doesn't change the ordering in terms of their real inside the block. Yeah. And yes, after I will use that in after this happens in the after two because I can skip all the comparisons inside the same block. If two codes are in the same block, I don't need to count disorders because they go in the lexicographic order anyway. So all the disorders are between two blocks. And there are a lot of disorders. And so the point is that I want to prove that if we have two blocks and they are disjoint by definition, and they are large because they have less than half of the coordinates specified, because we read less than half of the coordinates. Because if every block reads at least half the coordinates, then I have proven what I want to prove initially, and I don't need to go into the proof here. So I assume that all the blocks, or if at least one block has a lot of coordinates specified, I have proved the worst case is expensive. And if all the blocks have strictly less than half the coordinates specified, around half the coordinates written down, then I can do the proof using the fact that each two blocks have few specified coordinates. Let's just write the patterns one on top of the other. And I now for two blocks. Each of them has less than half the coordinates rounded down specified. That means that together they have, that means that it has at most half the coordinates rounded down minus 1 specified. Together they have at most all the coordinates minus 2 specified. That means that there are at least two common floating coordinates. there are at least two coordinates where neither block is specified. Because for every block, there are fixed coordinates, specified coordinates, checked coordinates, and there are free coordinates, which are inside the block. And they have at least two common free coordinates. And now I will just enumerate all the inversions between these two blocks and show that for that I basically split everything into pairs. I will build an evolution such that pairs of codes will correspond to pairs of codes which compare the same, and this will prove that there is an even number of inversions and there is an even number of non-inversions.
You just mean that if two strings are one is smaller than the other, then you can you can change the second.
Yes.
And it will not change the order.
Yes. Yeah. The point is that I have these three coordinates, common three coordinates, and now I ask, okay, give me two strings. Where is the first difference? So what are the options? It can be before here. In this case, I can flip this bit, and this is an involution, and it is invariant in terms of where the first difference is, and the comparison doesn't change, and I have my involution. Okay, I can say the first difference is here, in the first common free coordinate. But I have the second common free coordinate, I can just flip bits here. Maybe the first difference is here, but then I have either 0, 0 or 1, 1 here. But if I have 0, 0, I can put 1, 1 here with the same first difference. And if I have 1, 1, I can put 0, 0 with the same first difference. So the idea is that I ask so like that I build an involution, and this involution preserves the comparison between two codes, and this means that I see now that I have an even number of insertions.
I just don't understand why you need 2 bits.
Why 2 bits? Because otherwise the problem is if I have the first difference is here, I need to do something. If I just ask to have 2 bits, I still have linear lower bound, and I have a simple proof in this case. Otherwise, it is falling. It says written, and I need to do some juggling. I'm not sure how to do it. The worst case is like that. The worst case which I want to avoid. I have a single common bit here, a common 3 bit here, and all the other 3 bits are before. In this case, I cannot change anything on the left because this will break the first difference. And I can't change anything here because it is already the first difference. And so I cannot change anything. And technically, it is possible to build a counterexample to what I would like to use as a technical statement here. So there is no involution, and then I need to find a different proof, and I don't want to do that. And if I have the second, I don't have any complicated combinatorics. I just say, okay, I flip here. And so, what I have just proven by this case-by-case analysis, I have checked that if we have 2 blocks, well, also, what I didn't say aloud. I didn't say aloud that I must have the first difference somewhere because the blocks are not intersecting. Well, it would be very annoying for my proof, but they are not intersecting. So what I have shown, if we take 2 non-intersecting blocks, the number of inversions such that I is from one block and J is from the other block is even. If they have at least two common free positions, common free coordinates. And this means that if my binary decision tree had the height less than half number of the bits rounded down, then my after permutation and before permutation will be even permutation. But then the increment permutation will be even permutation, and in particular, it will fail to be an even length cycle, which is an odd permutation.
So Sasha asks that whether in this chaos, at least one can understand the sacred role of n over 2. And I think that thing I have understood. So the sacred role of n over 2 is that n over 2 plus n over 2 is n.
Yes.
Smaller.
Most n.
Okay, it must n.
Yes, but this is true. It's true that n over 2 here is a bit technical thing just to draw this picture. It is necessary to draw this picture for free.
So, actually, you are using that two sets having less than n over 2 elements can't, I mean, their union can't cover their
Yes.
total universe.
Yes.
And over 2 is used to show that the permutations are even.
Yeah, well, yes, that's the global one.
Because we can just clear all inversions in some ways so that the number of inversions is even. Using this.
Could you read why we have arbitrary options inside the block, especially in after permutation?
Okay, in the after permutation, if we have an inversion inside the block, let us draw the schema of this inversion somewhere. So these are the coordinates that are fixed, that have been read. And okay, and they are the same, of course they are the same in all the codes inside the block. Okay, so here is the first difference, for example. I must have first difference somewhere. Okay, and now I ask, were they, before I applied increment, in the before case, they were in order because they were enumerated lexicographically. But now I have changed the same positions in the same way in both codes. In the same way because the fixed positions are changed in the same way.
Yes.
And if they were in lexicographically correct order before, after changing the same positions in the same way, they will still be lexicographically correct order.
And because you
basically, if you have x smaller than y, and then add 10 to both, x plus 10 is still smaller than y plus 10.
Y plus.
Why? Because in reality, when I just change the same positions in the same way,
Yes.
if I change it from 0 to 1, I just add to all the elements inside the block the corresponding power of 2. If I change from 1 to 0, I subtract the corresponding power of 2.
Yes, but suppose we have two elements which have some free bit and they was different.
Yes, but the difference between the free bits doesn't change because of this addition. And initially they were in the lexicographic order.
They can be different, and after that, after changes, they can become equal.
No, they are in the same. They are in the same block, and so the differences are in the positions which are not altered. Because as we said, when we do the increment, because we need to have a permutation, we cannot write what we haven't read. And this means that we cannot change the positions which are not the defining positions of the block.
Okay, then the problem that I didn't understand why we can't change something that we didn't read.
It was in the beginning, because if we change something which we didn't read,
Yes.
we can imagine the situation which is different only in the position we have changed blindly.
Yes.
And this cannot affect, as we haven't read this position,
Yes.
this difference doesn't change our decision. And
Yes.
if we write this position, then we destroy this difference. And if we destroy the difference, it is not bijective.
I see.
And then we run out of codes. Okay, any other questions?
It was not very clear for everybody.
For me, it was
Yeah. I'm surprised that there are two people, at least two people.
at least two. So not for a while, it was not.
Well, the problem is that there is basically almost nothing going on. There is just juggling of notions.
Maybe I could understand, but Shane kept me distracted. Actually, it was there are two sides of Shane's absence. Yeah, one that he keeps distracting, but usually this distracts everybody. But now it distracts only myself. And the second that after this question, the exposition becomes more clear. And also. Okay, so have you finished?
Yeah, well, I can also maybe mention that I don't know if this paper has been finally fully published, but there is a construction which says, okay, if we have not bits, but some odd number of states for every position, and if you go from 2 elements to n, and from n bits to, for example, n3 state digit, the n ternary digits, then there exists indeed a way to have a binary count, ternary counter, read very few bits, or very many bits, because then this obstacle of parity doesn't apply. It is indeed enough to get rid of this parity. Ternary counter.
Okay, Slava, understand?
I think yes.
Yes? Uh-huh.
So it seems that you cannot go further than you do with this.
Well, in this construction, if I don't go over N/2, I can do basic algebra and very simple combinatorics, basic permutation algebra and very simple combinatorics, because here I just need to do case-by-case analysis of 3 cases. If I go over N/2, then probably there is some proof, it seems true, but I'm not sure. But the problem is that there, well, you cannot do things for free, and there is global combinatorics. In the sense that two specific blocks can be in any relation they want, but there seems to be a global combinatorics problem, but I cannot formulate this global combinatorics problem. Of course, no, cannot prove it.
It would be that the correct bound is -1.
I believe that the correct bound is n minus small o of n. I don't really believe that one is universally correct constant, but I don't know what is the true correct bound. I guess it is even below polynomial, but I'm not sure. But that is just the gut feeling. Yeah.
Okay, thank you.